So our speaker today is Vicki Pedone. Vicki is, of course, a member of ICL. She is the co-chair of the curriculum committee and also comes early and helps set up the screen and stuff like that. So we appreciate all the work that Vicki does. Vicki is a geologist, has her PhD from SUNY Stony Brook, bachelor's from Smith College, and PhD from Stony Brook, and worked at a couple of other places, but Cal State Northridge was the main place, I believe. And she has, one of the nice things about her profession is she really gets to travel a lot. She has done a lot of work, I know, in Utah and in Australia, and has gotten to travel quite a bit to various places doing research. In addition to that, she is a wine connoisseur and has taken many trips to sample various wines. So here's Vicki.
Okay, thank you, John. We've got wine in here just in case. Well, there have been times in Earth history. Sorry, your thing. Okay, can you hear now? Okay. There have been times in Earth history when the average global temperature has either been warmer, significantly warmer, or cooler than today. Such times in Earth's past have sometimes been used by those who wish to deny or obfuscate that humans are causing climate change because these changes occurred before humans existed. Today I'm going to talk about the factors that help regulate Earth's temperature and illustrate with two examples from the past, and then reflect on what do paleoclimate studies teach us about today's climate change. I want to start off by saying that climate science is not new. It's not a science that was only born about 50 years ago. Joseph Henry, in 1856, at the annual meeting of the American Academy of Science, delivered a paper. Henry was an eminent physicist, inventor, the first secretary of the Smithsonian. So he had a lot of clout as a scientist of that time. In his talk, there was this quote: "An atmosphere of that gas, CO2, would give to our Earth a high temperature, and as if some suppose, at one period of its history, the Earth had mixed with it a larger proportion than at present, and increased temperature must have necessarily resulted." But Joseph Henry was not the scientist that performed the experiments, nor was he the author of that paper. The author of the paper affecting the heat of the sun's rays was Eunice Foote. She was an amateur scientist and a women's rights activist. Her experiments compared the temperatures in cylinders filled with different gases, which led her to the conclusion that Earth would have been warmer in the past if CO2 levels were higher. Eunice Foote was not allowed to read her paper because she was a woman. Henry, in his acknowledgement when he presented the talk, did say, "This is the work of Mrs. Eunice Foote," stating that science was of no country and of no sex. Eunice Foote was the first person to postulate the theory, although the credit is given to John Tyndall, who published similar results about 5 years later. Her work was only recently rediscovered because the American Academy of Science did not publish the paper because it was written by a woman. So I thought it was a fitting story to tell you on this last day of Women's History Month. Well, the Earth is 4.6 billion years old, but I'm only going to talk about the last 500 million years, and actually a very small portion of that. Okay. And the reason is it took 4 billion years for the Earth to become, quote, modern, for the sun luminosity, for the atmosphere, hydrosphere, geosphere, biosphere to be somewhat similar to they are today. In other words, to be like modern Earth. So I'm going to look at the factors that have helped regulate climate just during the past 500 million. So the first thing I'm going to talk about are the 3 astronomical cycles that result in a change in the Earth-Sun relationship. The first is eccentricity. The Earth's orbit around the Sun changes from nearly circular to more elliptical on a period of about 100,000 years. The second cycle is obliquity, or the change in the tilt of the Earth's axis from about 22 degrees to 24.5 degrees, and this occurs on a period of about 41,000 years. And the last is precession. The Earth wobbles like a spinning top, so its axis makes this little circle on a cycle of about 26,000 years. These are regular, predictable intervals called Milankovitch cycles. These changes, as they occur throughout time, don't cause much change to solar radiation at the equator. The equator basically receives the same amount of solar radiation regardless of what these cycles are doing. However, they significantly affect the high latitudes, the polar regions. They change the amount of solar radiation received at the poles, so sometimes the poles are warmer or colder than average. I'm going to spend quite a bit of time talking about the greenhouse gases in the lower atmosphere. Sunlight consists of about 50% visible light and 50% infrared light. Gas molecules in the atmosphere do not interact with visible light. Small amounts of this are either reflected back to space or by surfaces on the Earth. However, most of the visible light hits the Earth's surface. It's absorbed by the Earth's surface, and then some of it is radiated back as infrared thermal heat. Some of the infrared energy in sunlight is absorbed by molecules in the atmosphere. These certain molecules that can do this are called greenhouse gases. And in Earth, the most abundant ones are water vapor, carbon dioxide, and methane. So these gases absorb the infrared energy from sunlight and then some from what's radiated back from the Earth. Okay. Greenhouse gases are not evil substances. The average surface temperature today is about 59 degrees. If there were no greenhouse gases in the atmosphere, the surface of the Earth would be 0 degrees Fahrenheit. Earth would be an ice ball. The modern atmosphere consists mostly of nitrogen, followed by oxygen with a little bit of argon, and only 0.1% of trace gases. But we see a gas every day in the atmosphere that forms a lot more than 0.1%. Clouds, water vapor. It can form up to 4% of the atmosphere. Why isn't it included? Water vapor is the most abundant greenhouse gas. It's responsible for 50 to 60% of the greenhouse effect. Water vapor in the atmosphere is currently increasing because the temperature of the atmosphere is getting warmer. Warm air can hold more water vapor than cold air. In fact, a 1 degree centigrade increase in temperature can cause a 7% increase in water vapor. Aha! So it's not humans, after all. We are not the villains. It's not the CO2 that we add to the atmosphere. It's water vapor. Those seeking to put the blame on natural systems and not on human activities for causing climate change point to water through the lack of understanding of the science. Water is fundamentally different than any other atmospheric gas. It is condensable. Water vapor, when water vapor is cooled, it changes from gas to liquid. No other gas in the atmosphere does that. Water vapor is part of a positive feedback cycle. So as temperature increases, this causes more evaporation in the ocean, which puts water vapor into the atmosphere, which makes the atmosphere hotter. So temperature increases, which causes more evaporation, and so on and so on. So you create a cycle that feeds on itself. Although water is the major player in the greenhouse effect, it is not the driver of the system. It does not trigger the initial heating that starts the feedback loop. Something else has to trigger that initial heating. The main greenhouse gas driver of climate is carbon dioxide. Carbon dioxide is the major component of the trace gases, followed by methane. What do they want to say about this? So what I wanted to point out here, yes, was that even though it's less than 0.1% of the atmosphere, as is methane, even smaller, they punch well above their weight in the effect that they cause in global warming. There are two more important things to consider about greenhouse gases. Those are the residence time and their global warming potential. Residence time is how long a gas stays in the atmosphere before physical or chemical processes remove it. Okay. Water vapor has a very short residence time. It does not hang around in the atmosphere. Methane lasts about 12 years, but carbon dioxide, hundreds to thousands of years. Another important thing is their global warming potential. So this is, it depends on how strongly a gas absorbs infrared energy and its residence time. Global warming potentials are always compared to CO2, so we set CO2 to 1. Gases that have less than 1 have less potential, and those with more, higher numbers have more potential. Okay. Water has a very low global warming potential. Guess why? Because of its residence time. Doesn't hang around long enough. Without other gases to continue to cause the warming, water vapor just comes right out. Okay. Methane, on the other hand, has a relatively short residence time, but it has a high global warming potential because it's a strong absorber of infrared energy. So the impact of methane depends on how long a period of time significant amounts are added to the atmosphere. If it's only a short spike, it's going to come out fairly quickly and not cause a long-term heating. But if you keep adding methane over a long period, it can cause a significant warming. So it's carbon dioxide, really, because of its relatively high abundance as a trace gas and its incredibly long residence time that makes it the gas of most concern. The third factor is albedo, not libido. When viewed from space, Earth presents a variety of colors, from dark oceans and forested areas to light-colored ice and deserts. When solar energy strikes a surface, it is either absorbed or reflected. Albedo is the percent of solar radiation that's reflected. So surfaces with high albedo reflect a lot of sunlight. Those with low albedo absorb a lot of solar radiation. Clearly, the more solar radiation that is absorbed, the warmer Earth is going to be. The modern Earth has a global albedo of about 30%. Here are some numbers for common Earth materials for the albedo of common surfaces. So you can see that the light-colored material, ice, light-colored rocks, bare grounds, deserts, have higher numbers, with ice being the best reflector. And dark-colored material and water have the lowest albedo. They absorb the most, with water being the best absorber. Water not only is our greatest absorber of solar energy, it has a remarkably high heat capacity. And what does that mean? Well, it means it takes a lot of energy to increase its temperature, to heat it up. A good example of that is picture yourself on a summer day at the beach. Nice hot summer day. You've been lying on your blanket getting very hot. So you said, it's time to go into the water. So you get up off your blanket and you first step on the sand and you start to hop like a bunny, going madly to the ocean because your feet are burning on the sand. You step into the little 1 inch of water and it's immediately cool. Okay. Well, the water and the sand have been absorbing the same amount of solar radiation all the time you've been lying there on your blanket, but the water has not heated up much. It's been absorbing and storing the energy and not converting it into the temperature of the water. So to look at that quantitatively, it takes a little over 4 joules of energy to raise 1 gram of water 1 degree centigrade. Well, it doesn't mean anything unless you compare it to something else familiar. So let's look at soil or that sand. It takes less than 1 joule to raise it 1 gram 1 degree centigrade. So what that means, the high heat capacity, why it's important, is it means that water absorbs a lot of heat and stores it. It holds it. It also releases it slowly. So it's the perfect storage system of heat that prevents global climate from wild temperature fluctuations. It's also why it's used for passive solar heating. Okay. Well, what does this mean to albedo? Seems like a little tangent I've gone off on. Well, what's important is to know that the level of sea level has changed significantly through geologic time. So you can see where sea level is today. We're kind of now aware of this because of the melting of land ice. We're aware that sea level is rising. So if all land ice melted today, sea level will rise another 200 feet. Okay, so that's where sea level would be. Okay. Well, you can see on this curve that there are lots of times in Earth history when sea level's been a lot higher than that. Okay. So the main driver of sea level change is plate tectonics, followed by the volume of land ice and the thermal expansion of water. For example, if we look at the time period of about 150 million years to 40 million years, sea level was 600 or more feet higher than it is today. Well, what would the Earth look like at that point? Okay, so during this ice-free time, there were numerous shallow seas, shown in light blue. You can see a seaway divides the entire continent of North America. Many shallow seas, so much water at the Earth's surface. Remember, water is our absorber. So the albedo of Earth was very low during this time, contributing to warming of the Earth. A fourth factor is ocean circulation. The world ocean holds far more heat and far more carbon dioxide than does the atmosphere. By absorbing, storing, and moving massive amounts of heat and carbon dioxide, the ocean acts as a vital buffer in regulating wild changes in Earth temperature and in CO2 levels. The physical structure of the ocean can be simplified into two components. The first is surface water. That is the water that is directly affected by sunlight. In other words, it's the depth to which water can penetrate. And it's shown here in this diagram in the colors yellow to red. Everything else on this diagram, the green, blues, and purples, are all bottom water. The average temperature of the global ocean today is 38 degrees Fahrenheit. And it's pretty cold. Okay. So, yes. The surface of the currents of the ocean move along the surface in large gyres and circles, moving in the direction depending on the Coriolis effect in the northern and southern hemisphere. This is surface water driven by the wind. Okay, that's what's making the gyres go. Okay, they cool in the high latitudes, they warm in the equatorial regions, so they are really key in distributing heat from the equator to the higher latitudes. The one exception is shown there at the bottom. If you look at the current that flows around Antarctica, it's all cold. It doesn't have any warm surface temperature. This is the Antarctic circumpolar current. Note that it pushes any water coming down from the Indian, Atlantic, or Pacific, if it's warm, gets deflected back toward the equator. So this current is key in keeping Antarctica the coldest place on Earth. However, most of the water is not wind-driven surface water. Okay, it's the bottom water. It also moves but vertically and horizontally. It's driven by density. Salty water is denser than fresh water. Cold water is denser than warm water. Okay. As seawater freezes to form ice, and as water evaporates to form water vapor, it leaves behind salt. So at high latitudes, cold, salty water sinks vertically. In this diagram of the Atlantic Ocean, we can see cold, salty bottom water formed near Antarctica, sinking and moving along the ocean bottom. In the North Atlantic, we see that this type of water, cold, salty water, formed at Greenland, sinks and moves horizontally, rising near Greenland because it flows over the even denser Antarctic bottom water. The global ocean circulation is a combination of the surface wind-driven circulation and the density-driven circulation of the deep water. It is greatly simplified as the global ocean conveyor belt. In this diagram, yes, the red represents flow on the surface, and the blue represents flow in the deep water. And yes, it is generally true that the flow on the surface is also warmer. However, I do want to point out that this red current flowing around Antarctica is not warm, okay? It is cold. Okay. The conveyor is powered by the formation of deep water at 2 locations in the Antarctic, you see them labeled on the diagram, and at 2 locations in the North Atlantic. Okay. The huge masses of deep water in the Pacific and Indian Ocean are formed near Antarctica, and the bottom water in the Atlantic Ocean is mostly from the North Atlantic. On average, it takes a water molecule about 1,000 years to make a complete trip on the conveyor. So let's look back at, we know this is a warm period. This is our late Cretaceous. And we see that abundant fossil and geochemical records indicate that both the surface and the bottom waters of the ocean were much warmer than today. Just as a reminder, today's ocean, 38 degrees Fahrenheit. The Cretaceous ocean is estimated to be about 58 degrees Fahrenheit, 20 degrees warmer. Okay. So certainly the ocean had a form of circulation that helped move heat from the equator to the poles, but it's unlikely to be similar to the conveyor belt that we have today. Energy stored in the Cretaceous ocean contributed to it being much warmer. And the last factor I'll talk about is plate tectonics. Plate tectonics directly or indirectly affects every relationship up here except the Earth-Sun relationship. Okay. During times of high levels of plate activity, there are numerous large mid-ocean ridges. They take up a lot of space in the ocean, so they displace water. And that water moves up, floods low-lying parts of the continents, creating vast shallow seas, which you've seen in those other pictures. The more water, the more energy absorbed, the warmer it is. Active plate motions also cause intense and widespread volcanism, both in the subduction zones and in the mid-ocean ridges. Well, the volcanism emits lots of carbon dioxide into the atmosphere and into the ocean, some of which makes it back to the atmosphere. So again, more greenhouse gas. So times of high plate activity levels are characterized by being the warm intervals in Earth history. Well, times of low levels obviously are the opposite, and why? The mid-ocean ridges shrink. They become much smaller, they take up less space, so the water goes back into the ocean. So the continental shelves become dry land, and that increases the amount reflected, so it increases albedo, which causes cooling. There's less volcanism, so there's less input of CO2 into the atmosphere. The other thing about low levels of activity is that you're not adding CO2, but you've raised up mountains during times of convergence, you have mountain range. Well, they're still going to have mineral weathering. And mineral weathering removes carbon dioxide. So when you're not adding it, but you're taking it away here. So these are times, cooler times in Earth history. So all taken together, the factors that help regulate global climate not only affect temperature, but of course they affect the distribution of rainfall and the frequency and severity of major storms. These complex interactions can at times occur at times where they cancel each other out and help minimize the effects, or they can all come together when they all are trying to do cool or hot, and that way they combine and they amplify their effects. When we look at the climate history of the past 500 million years, we see mostly green. Okay. These are called greenhouse phases, or they're green, indicating a warm, ice-free Earth. Okay. The icehouse phases, in kind of the pale blue to really pale green, form only 20 to 25% of the last 500 million years. There are only 3 of them. There are only 3 icehouse phases. We happen to live in one of them, which is why I'm going to spend a lot of time on it. Okay. These are times, icehouse phases are times when ice existed at least episodically at one pole. And if you look at those 3 icehouse phases, only the last one, the one we're in now, has ice at both poles. Okay. Well, I'm sure that red always attracts your attention, so I'm sure that one red thing stands out and you're going, well, what's that one? Okay, so that's a time of hot, dry Earth. It was the Triassic period from about 250 to 200 million years ago. The levels of CO2 in the atmosphere were extremely high because there was a large eruption of a volcanic terrain in Siberia right before the start of the Triassic. At least 300 million square miles of volcanic rock were erupted then. Okay. The supercontinent of Pangaea was also in existence, and the continental interior was so far away from the influence of the ocean that it was largely dry. An important thing to consider in comparing icehouse and greenhouse phases is the difference in temperature between the equator and the pole. Today, the average temperature at the equator is about 85 degrees. Near the Arctic Circle, in non-coastal areas, it's about 20, and at the North Pole, about -5. So that gives us a temperature gradient of 90 degrees, which is fairly steep. And what that does is make the climate belts fairly narrow and increasingly severe toward the pole. So we know what they are today. We have tropical, subtropical, temperate, and polar. But what about our Cretaceous world at 100 million years, which we know was ice-free with lots of shallow seas? The temperature at the equator was at least 90 degrees, maybe a little warmer even. And near the Arctic Circle, about 55, and the pole, 40. Because remember, ice-free. So with a relatively gentle temperature gradient, climate belts are very broad and mild. There were semi-tropical vegetation and dinosaurs that lived at the latitude of Anchorage, Oslo, and Leningrad today. And also then temperate climate, flora and fauna, lived much closer to the poles than they do today. Okay. So before I start looking at some times of Earth history, there is something really important that I want to point out to you that I don't think enough scientists do in their presentations. I need to point out that real measurements, direct data of important things to climate like temperature and CO2 levels, exist for only the tiniest, 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 tiniest portion of 500 million years. Humans have been keeping temperature readings from thermometers 300 years. CO2 concentrations, we actually have better measurements on those because we have air bubbles trapped in ice cores, and we have real measurements for about 800,000 years. Okay, that's pretty small compared to 500 million. So when scientists, including me, glibly put up these graphs, here's global temperature for the last 485 million years. And here are CO2 levels for the past 400 million years. You should ask yourself, how do they know that? And you should ask yourself, how well do they know that? Okay. Almost every point on that graph came from a proxy. Okay. So, proxies provide indirect evidence that act as a substitute for direct instrumental measurements. Paleoclimatologists use physical, chemical, and biological features to reconstruct past climate. So how much we trust these graphs is dependent on how much we trust the proxies. Misunderstanding and sometimes misuse of proxies can fuel climate change denial. Common types of proxies are tree rings, features of fossils, pollen, sediment characteristics, lots of geochemical materials, isotope ratios, the types and changes in organic molecules. It would take several college courses to go through all the different proxies that are used to reconstruct climate. Each of them has a degree of uncertainty. Many of them are regional in scope, and some of them are specific only to certain geologic time periods. Graphs like this one of average global temperature, which is on the y-axis, have been assembled from numerous different proxies in time and space from studies in top peer-reviewed papers. And these compilations are frequently reevaluated and updated. Okay. The gray shading around the temperature shows the levels of uncertainty, and the black line is the average solution. I wanted to show this so you can see for yourself the degree of uncertainty which that comes from the proxy record of temperature. The other important component on this graph on the x-axis is time. Well, that has its own set of issues. Determining an accurate absolute time in the ancient physical record always has a degree of uncertainty, which increases with increasing age. Even a 1% error at 100 million years is a million years. Okay. The science of paleoclimatology must grapple with three components. Understanding the climate system. What drives it? How are these components related? How well do we understand feedback loops and climate drivers in all geologic times, greenhouse and icehouse? In what ways and to what level can we resolve time in the physical record? And proxies, what constitute a climate-related proxy in the physical record, and how reliable is it? So I'm going to start with one example in Earth history when climate was hotter. It shouldn't surprise you that it's the Cretaceous, because I've been showing it over and over, okay? So the Cretaceous greenhouse is often termed a hothouse or a super greenhouse because it is thought to be one of the hottest times in geologic history in the past 500 million years. It occurred from about 125 to 85 million years ago with peak heat at about 100 million years. So here is the Cretaceous world. The continents have been moving apart for about 125 million years since the beginning of the breakup of Pangaea. We see that North America has just separated from Europe. Greenland is still part of North America, part of Canada, and not the US. North America and South America are far apart. South America and Africa have separated, and the Arabian Peninsula is still connected to Africa. What may surprise you is there is India. India is far in the southern hemisphere, and Antarctica and Australia form one large continent situated on the ice-free South Pole. High levels of plate tectonic activity following the breakup of Pangaea resulted in the high global sea level, making this Cretaceous Earth much hotter because it has a very low albedo. Greenhouse gases also were emitted by volcanism emitted by the mid-ocean ridges and subduction zones. And the hotter you get, remember, the more water vapor you put into the atmosphere. So the temperature of the Cretaceous ocean, as I had put up before, was about 20 degrees warmer than today. And warm surface and bottom water circulated at high latitudes. And this is part of what keep them ice-free. Okay. Well-dated fossil specimens from multiple continents indicate that the flora and fauna adapted to subtropical and temperate climates lived far more north and south of those zones than they do today because of the gentle temperature gradient. These help confirm a warm Earth. Well, how hot was it? Some paleoclimate proxies suggest that the Cretaceous hothouse had a peak global mean temperature, not peak temperature, not the highest temperature in the year, mean temperature of 97 degrees Fahrenheit. Wow, that is really hot. Other suggestions for this period put it at more like 86 degrees Fahrenheit, which is still, when we compare it, even in 2024, when we think about how hot it's getting, it's 59 degrees. Okay. So possibly the peak mean might have been well into the 90s, or maybe some of the proxy measurements are strongly seasonally biased based on properties formed in summer months. Whatever, abundant fossil evidence tells us that Earth was much warmer during the Cretaceous. It is very likely that organisms that evolve in a greenhouse or hothouse world are far better adapted to withstand extreme heat than the plants and animals alive today. If you were put back down in that world, you would probably find it unbearably hot, even though it looks very nice. Okay. So here's the vision of the fern and palm tree filled world of the late Cretaceous. There's even a little group of dinosaurs crossing the river here. Volcanoes in the background are happily pumping away CO2 into this already warm Earth. So, if you Google, why was the Cretaceous hothouse phase so hot, which of course I did, you get a very reasonable answer. The Cretaceous hothouse was exceptionally hot, primarily due to an intense greenhouse effect driven by extremely high atmospheric CO2 levels. Great, all makes sense. So let's look what the proxy data say. Okay. Proxy-derived data for the Cretaceous hothouse do show a maximum of 1,200 ppm carbon dioxide. That is 4 times higher than the pre-industrial level and 3 times higher than today. Okay. But you also see that there's a drop at about 90 million years. During the Cretaceous, oceans experienced multiple oceanic anoxic events, OAEs, okay, during which the bottom waters of the oceans, those vast bottom waters, became totally devoid of oxygen. This prevented the aerobic decomposition of the vast rain of all the dead cyanobacteria, the dead algae, the dead anything living in the surface waters. Okay. So their abundant organic matter accumulated on the bottoms of the shallow seas and deep oceans, sequestering the carbon of the dead marine organisms instead of returning it to the carbon cycle via aerobic decomposition. And by the way, these organic-rich deposits of the Cretaceous account for the formation of much of the world's petroleum deposits, which have absolutely nothing to do with dinosaurs. Okay. So the OAEs events, and the early ones, might have kept the CO2 level from going even higher, and the OAE2 is thought responsible for that drop in the CO2 levels. Okay. So if burial of organic carbon reduced CO2 levels, then global temperatures should drop, right? Well, if we carefully compare the temperature and CO2 graphs, we see that the temperature maximum occurs at a time when CO2 was dropping. This just doesn't seem to make sense. Okay. The mismatch is probably saying one of two things or both. There might be a time lag between the response in temperature to changes in CO2, especially in a super greenhouse world. As creatures of the ice house, we have less certain knowledge of how climate functions in a greenhouse Earth, where there might be different feedback loops that we just have not recognized yet. The mismatch may also be showing that proxy information and absolute dating do not have enough fidelity to resolve ambiguities on a fine time scale. The data are not useless. They give us a vision of a greenhouse world, what Earth is like when the climate is much hotter. But what we can't do is use them to make quantitative comparisons to today's climate change. For that, we need to look at more recent times, which we'll do after the break.
Questions? Got
Yes,
one.
I just want you to know we're unable to change a lot of the lighting in here, so.
Let me start with one, Vicki.
Okay.
So what caused the deep oceans to turn anoxic there at that period, allowing the formation of the fossil fuels. Was it related to the ocean depth? Because I know you said there was
No.
650 feet. Would that,
No, it wasn't depth. I don't know. Anybody know?
What about,
I will look it up, and I will let you know what caused the anoxic events.
pure speculation, could have
I
been.
think it's
current-
stagnation, too, yeah.
Yes, that's what I was going
I
to say.
think it's stagnation. It slowed down, and it just, yeah.
Thank you, Vicki. The biggest impact to me of this talk, and I learned many things from you today, was the significance of plate tectonics and volcanism on the, and I knew a bit about volcanism.
Sure.
But here's my question. What do we know about the cycles of the plate tectonics and volcanic periods of activity? Because that's a closed system, the Earth is, pretty much. All that stuff is occurring inside, not affected by the outside. And moreover, the material that we have sticks around for a long time, basalt. So we should have some data about, is there a cycle? And or cycles, and what are they?
Well, I mean, there's a short carbon cycle and a long carbon cycle. And the long carbon cycle involves plate tectonics, in which rocks, like carbonate rocks that have, of course, lots of carbon in them, as well as any coal or whatever, when they're subducted back into the earth, the carbon goes back into the earth, which ultimately gets emitted by volcanoes. And that's a very slow carbon system. And then there's the fast carbon system, which is all the organic matter at the surface of the earth and in the atmosphere. Does that answer your question? No.
I know it's not a follow-up. I'm really interested in the volcanic, not subduction so much as the spreading of the ocean floor, which led to shallow seas. Now, it sounds like this happens periodically. We get a lot of volcanic activity.
Oh, yeah.
And is there any cycle to that? That's what I'm asking.
Not a regular cycle, no. The plate tectonic, the plate motions, you don't get every 250 million years, you get high plate activity and everything. It's not cyclic in that nature.
Hi, Vicki. Wonderful presentation. I was reading my Bible yesterday in Genesis, and I was just trying to do the math. I was trying to figure out where does Adam fit on this chronology, and what are the plus and minuses on Adam?
Oh, he's going to be in one of the next upcoming slides.
so another question, while we wait for others here. How did the sea levels get to be 650 feet higher? I mean, right now, if all the ice melted on the planet, the sea levels would only rise to 220 feet.
Yeah.
Why the difference?
The plate
in the
tectonic,
ages?
it's the mid-ocean ridges. That
much,
it's funny,
wow.
people don't really think about it that much, but who was the Greek in the bathtub? Archimedes. Okay, the Archimedes principle. Okay, when you get into a bathtub or you throw something big into a big thing of water, what happens to the level of the water? What happens when you put many huge mid-ocean ridges on the bottom of the ocean? Water gets displaced up and floods. So it has far more effect. They have look at think of the volume of a mid-ocean ridge that might go thousands of miles. It's so much bigger than an ice sheet. Okay, so that's the plate tectonics are the main causer of major changes in sea level.
Hi, this is awesome. Thank you. You said mineralization, mineral weatherization or something that actually takes back the carbon
Yeah.
as like an opposite effect of the ridges building.
Right.
I've never heard of that, and I'm wondering if you can talk a little bit more about
Yeah,
that.
I'm going to actually show a slide in the second half that'll have the chemical formula, which show how when the minerals break down, one of the things they need as they break apart is carbon dioxide. So they take that from the atmosphere, and then they give off calcium and other, water and other things. But they need where they take the CO2 from that action. It's a weak acid, so it helps the mineral weathering, and we'll see that it had one of the big effects in changing Earth climate to an ice house.
If I can answer for Mark's question, in
Yeah.
the New Yorker cartoon today or yesterday had the whole group going through the parting of the sea, and one of the men in the crowd said, "I wouldn't have gone this way."
Love that.
I wouldn't have gone this way. Okay, I guess we'll take our 10-minute break. We'll start again at about 11:05.
Okay, so now we're going to look at the time. Is this microphone still okay? Okay, now we're going to look at the time of which we are a part. The greenhouse conditions, whoops. It makes it go up. Let me try spacebar. Spacebar, I'll just hit spacebar. Okay, the greenhouse conditions that began in the Jurassic period continued into the Cenozoic era until about 34 million years ago, when the planet entered the late Cenozoic ice age that persists to today. So what happened to make Earth change from greenhouse to ice house? Plate tectonic events are the cause of the change. And here I'm going to make a brief diversion to answer Mark's question. The entire evolution of the human lineage, that of the hominins, took place in the last 7 to 8 million years of the late Cenozoic ice age. And our genus Homo took place in the last 2.5 million years, the coldest part of the ice age. Okay. I point this out now because Homo sapiens are likely to be the cause of Earth changing from ice house to greenhouse. More on that later. Let's get back to plate tectonics. Okay. 3 major events occurred in the Cenozoic that changed the climate. The first started around 50 million years ago. Throughout the late Cretaceous and the early part of the Cenozoic, plate motions, the tectonic plate that contained the continent of India, moved northward. Remember, it was way down in the southern hemisphere, so it's making its way north. Okay. Between 50 and 40 million years ago, all of the ocean crust that had separated India from Asia had been subducted. So now the continent of India begins to collide with the continent of Asia. And remember that continental rocks cannot be subducted. So this collision then, what's it do? It results in uplift. So they crunch together, and they have uplifted the Himalayas and the huge region of the Tibetan Plateau, which unfortunately gets kind of cut off in this picture. Okay. So what effect did this have on climate? Well, uplift of mountains decreases atmospheric CO2, and that's kind of like, what? Okay, so here's what happens. It caused a dramatic increase in mineral weathering of silicate minerals, which make up igneous rocks, metamorphic rocks, as well as quite a few sedimentary rocks. So here's what happens during the weathering of these minerals, they need CO2. CO2 and water and the mineral combine to break down the mineral and send it off, and with simple equation, but a byproduct of quartz and other ions. Okay. So CO2 is removed from the atmosphere by mineral weathering. So during this long period, this 50-some million years we've had of convergence of India and Asia, has resulted in removal of CO2 by weathering, and you can see it's causing gradual cooling throughout this time. The next tectonic event that made a major change in ocean circulation, starting about 40 million years ago, that led to the growth of ice sheets on Antarctica. Around 40 million years ago, Australia and Antarctica had only recently separated, and the passage between them was not well developed. South America and Antarctica were still connected. So warm waters coming down from the equator warmed Antarctica. So even though it was sitting on the South Pole, it kept it warm and ice-free. However, between 40 and 35 million years ago, South America and Antarctica separated. What this has allowed is the creation of the Drake's Passage, which allows unrestricted clockwise flow of cold water around Antarctica. So here, the Antarctic Circumpolar Current is born. This current is the coldest, mightiest, and fastest current on Earth, reaching from the ocean surface to the ocean bottom, as measuring as much as 1,200 miles across. The development of the circumpolar current effectively isolated the Southern Ocean from the warm waters of the Pacific, Indian, and Atlantic Oceans. In an already cooling Earth, this region cooled significantly. Ice sheets started to form on Antarctica about 34 million years ago, marking the onset of the late Cenozoic Ice Age. So if you focus your attention on the orange box, you see that from about 28 to 15 million years ago, the temperature shown in the red line stops dropping. It kind of levels off between maybe 64, 68 degrees Fahrenheit on average. The Antarctic ice sheets stop growing, but they don't disappear. But you'll see that the northern hemisphere is still ice-free. Starting around 15 million years ago, yet another plate tectonic event caused another change to climate by creating the Isthmus of Panama. Prior to the formation of the isthmus, the Central American Seaway allowed movement of warm tropical water between the Atlantic and the Pacific. The formation of the isthmus was completed between 3 and 5 million years ago, forcing ocean currents into a new pathway. The Gulf Stream got warmer and stronger. This is the surface current that carries heat and moisture north along the east coast of North America, across the North Atlantic into northern Europe. If we think back on global the ocean conveyor belt, it was the formation of the isthmus that was important in creating modern ocean circulation. Cooling and evaporating of water from the Gulf Stream in the North Atlantic introduced the deep water formation in the North Atlantic, helping continue to power stronger this conveyor belt. The circulation pattern in the North Atlantic then is given a special name the Atlantic Meridional Overturning Circulation, which I am going to continue to only refer to as AMOC. Okay. And please don't think, we had a talk, I think, last year on AMOC, and you've probably heard and read about it. And please don't think that the AMOC that created 3 to 5 million years ago has happily continued unchanged until today, when the evil humans are having climate change and threatening its existence. Okay. It has changed numerous times in the past few million years. But an important aspect of AMOC at this time was that it introduced extra moisture into the Arctic. And this allowed the start of ice sheets in the northern hemisphere for the first time between 3 and 5 million years ago. Okay, this graph, which shows global average temperature on the y-axis and time for the last 5 million years on the x. Okay. It shows some very interesting features. We see only small wiggles starting at a few degrees Fahrenheit at about 5 million, and they become a little colder and a little bigger until you get to about 2.5 million years. This represents the period of the increasing influence of the closing of the Isthmus of Panama, the development of AMOC, and the development of ice sheets in the northern hemisphere. Between 2.5 and 1 million years ago, we see that there's a change. These wiggles get much bigger, and they start to have a regular period of occurrence that is about 41,000 years. Okay. And then there's another change at 1 million. Okay. The wiggles get really big, and the time between the peaks lengthens to about 100,000 years. Okay. So first, what do these oscillations in temperature mean in terms of an ice age? Okay, an ice age consists of glacial times, which are the cold periods of an ice age, in which there's lots of land ice in the northern hemisphere, and interglacial times that are the warm periods of an ice age, in which there's a low volume of land ice. Okay. This diagram focuses on the northern hemisphere for a reason. The ice sheets on Antarctica are partly insulated from change by the circumpolar current. So their glacial interglacial cycles are different than those in the northern hemisphere. They mostly change in terms of the volume and extent of sea ice. The northern hemisphere shows dramatic changes in land ice volumes. So what causes glacial interglacial periods? Well, now we come back to a factor that I've ignored up until now. The northern polar region is sensitive to changes in solar radiation that result from the Milankovitch cycles. Between 1 and 3 million years, the glacial interglacial peaks we looked at occurred at 41,000 intervals. Well, what do you see there that matches? Obliquity. So they matched very well to the changes in Earth's obliquity. But at about 1 million, remember there was a change. The cycles got further apart longer to about 100,000 years, so they match the eccentricity cycle. This was a real puzzle to paleoclimatologists because both of these cycles were always operating. Eccentricity and obliquity were always going on before and after these changes in pacing of the glaciers. So this was a real puzzle. The time shift is called the mid-Pleistocene transition at 1 million years. And the intensity of the ice ages got much stronger. Ice sheets developed that could last 100,000 years. Also, the wiggles got bigger. The change in temperature before this was maybe 4 to 7 degrees Fahrenheit. But during the later part of the cycles, after 1 million years, 10 to 15 degree swings, big swings in temperature. Okay. The cause of the mid-Pleistocene transition is supported by most researchers today. It has to do with the dynamics of ice sheets. The average thickness of the Greenland ice sheet is a little over a mile, 5,500 feet. Its maximum is 2.2 miles, 11,450 feet. And the whole central portion of the Greenland ice sheet is over 10,000 feet thick. Well, in order to build a large, thick, heavy mass of ice, it has to have a strong base. It has to have something it can stick to that's not going to slide and move. It is hypothesized that when ice sheets first started to form in the Arctic, that the rocks of the Arctic were overlain by a fairly good thickness of soils, talus, and weathered rock. These provide only a weak base, so as ice tries to build up on them, they start to slide. Okay, they can't give them a strong base. So it's thought that it took many interglacial cycles to finally kind of remove this weaker material until at about 1 million years, the rock exposed at the base was firm, hard, crystalline, fresh rock. The ice could adhere and stick to the rock, so it could start to build up great thicknesses before the ice started to flow. Okay. As the ice sheets grew larger, they created a positive feedback loop. They increased albedo. They started reflecting sunlight. That led to more cooling, which led to more ice, which led to more reflection, which led, and so on, so on. So you get these nice positive feedback loops we see over and over again in climate change. Okay. Let's zoom in on just the past 450,000 years, shown in the red box, and look at what the little wiggles inside the big wiggles mean. So to reorient ourselves, the low to high temperature fluctuations respond to the expansion and contraction of ice sheets, with major fluctuations occurring every 100,000 years. Okay. The shape of this curve, because it has so many little peaks and valleys, is called sawtooth. There have been 4 interglacial cycles in the past 450,000 years. Interglacial cycles range from about 10,000 to 30,000 years long. They have been as warm or warmer than the current interglacial that we are now in. The glacial cycles last much longer, 70 to 90,000 years. Another feature of the glacial cycles is that they're really bumpy. They have a lot of smaller up and downs in temperature that don't quite get as hot as, of course, the interglacials. Another feature that they have in common are really abrupt ends. These terminations always begin when the glacial periods were at or very near its maximum, when the ice was the most extensive, when it was the coldest. They go right from that period to the hottest periods of icehouse, the interglacials. You can see that by the steepness of those lines. Okay. Although ice sheets take about 70 to 90,000 years to reach their maximums, their terminations take less than 10,000. So what causes the demise so quickly of vast ice sheets in the northern hemisphere and the reduction of sea ice in Antarctica? The initial trigger is a small increase in solar radiation in the Arctic owing to the Milankovitch cycles. But this increase, this little bit of heating, is not even close enough to begin to melt vast ice sheets like that. But what it does do is trigger a bunch of feedback loops that amplify this initial warming. So retreat of sea ice, retreat of ice margins, reduces the amount of sunlight that's reflected, so more is absorbed, so that Earth begins to heat up more. When you warm the atmosphere and the ocean, you increase evaporation. And so you add more water vapor to the atmosphere, so you're adding a good greenhouse gas. As the oceans warm, they circulate faster. Wind patterns also contribute by causing upwelling in certain coastlines of deep water, and this also releases that carbon dioxide trapped in the deep ocean. So both of these things increase CO2. And feedback loop 4, permafrost thaws and decomposes, which releases carbon dioxide and methane into the atmosphere. So all of these feedback loops increase warming, and they concurrently greatly amplify that little initial warming caused by the changes in the Milankovitch cycles. During the change from glacial to interglacial, global temperatures increased about 44 degrees Fahrenheit. Carbon dioxide increased about 150 ppm, and sea level rose about 300 feet. So what caused, I also want to point out that there's really good correlation between temperature, the red curve, and carbon dioxide, the green curve. So it's clear that carbon dioxide is an important factor in climate change during an ice age. In fact, an ice age might be more sensitive to changes in CO2 than in a greenhouse world where the CO2 levels are already pretty high. So what causes an interglacial to end and start going back to a glacial? Again, the initial trigger is likely a minimum in solar radiation in the northern or in the Arctic region caused by Milankovitch cycles, and then those feedback loops that I just discussed start going in reverse. So as ice builds up, albedo increases, oceans cool, they hold more CO2, taking it from the atmosphere. Circulation slows down, trapping it in the deep ocean longer. Less evaporation of cooler waters decreases water vapor, and permafrost forms. Okay. The sawtooth pattern that you see here in the red temperature curve indicates that melting ice happens faster than its accumulation, leading to quicker warming and slower cooling. And the last thing to look at are all the little bumps inside the glacial periods. So we're going to focus just on the last glacial, which started about 120,000 years ago and ended 10,000 years ago. There are 25 short cycles of abrupt warming to gradual cooling with spans about 500 to 2,000 years. So what caused these? They had temperature swings of 10 to 27 degrees Fahrenheit. It's thought that they are caused by the abrupt on-off switching of AMOC. Okay. So it strengthens, it weakens, it strengthens and weakens, which has a big effect on global climate, and it also trips some other feedback loops. So it was plate tectonics that led us to the late Cenozoic Ice Age. The tectonic situation has not changed. The circumpolar current is still flowing, Himalayas are still rising, and the Isthmus of Panama still separates the Atlantic and Pacific Oceans. Therefore, according to the pattern of glacial interglacial cycles established 1 million years ago, we are currently in the middle, roughly, of an interglacial period. And we should expect cooling in about 10,000 years, with massive ice sheets at about 80,000 years. Sadly, this probably is not going to happen. Human emissions of carbon dioxide into the atmosphere have likely already diverted climate from its natural course. For the last 1 million years, CO2 levels have oscillated between 150 and 300 ppm as Earth's climate transitioned out of glacial interglacial times. On March 18, 2026, the measured level of CO2 was 429. And we know that this level is continuing to rise, although we don't yet know what the maximum will be. To initiate the next glacial, we have to decrease by 129 ppm plus whatever else is going to happen to get to the maximum, and to get to the point where we could start to have large ice sheets, we have to remove almost twice as much as what we had to in any previous cycle. What mechanism is there to remove twice as much CO2? Well, there isn't one. Okay. So there's no mechanism known under the current conditions. So as long as atmospheric CO2 remains above 300 ppm, the next change in Milankovitch cycles is unlikely going to trigger the next glacial. Besides going to a high amount of CO2 in the atmosphere, the rate at which this is happening is just staggering. From the start of the interglacial time, 10,000 years ago to about 1860s, CO2 levels were fairly constant at about 260 ppm. They started to increase in the 1960s, and the rate of increase just keeps getting faster. The increase in 2023 to 2024 was the largest single-year increase yet measured. These rates of increase have never been seen before in geologic history, never been documented anyway. The best rates that we have good data for are the past 800,000 years, because we have actual CO2 measurements from ice cores for that time. The highest rate measured for that interval is 0.25 ppm per year. So we are currently increasing about 10 times faster than the fastest level, and 100 times faster than the average for the whole glacial time. Hotter greenhouse phases, usually the hothouse phase, of Earth history have CO2 levels greater than 800 ppm. The temperature proxies during those times, such as the late Cretaceous hothouse that we looked at, experience significantly higher temperatures than we currently experience in our world for longer times over larger regions. If our carbon emissions continue at the rate they are now, atmospheric CO2 could reach 800 ppm in less than 200 years. And remember, CO2 has residence times of hundreds to thousands of years, so heating will not cease or diminish quickly when we reduce carbon emissions. So what are the impacts of a warming Earth? AMOC is unstable. Melting of ice in the Arctic may weaken it. Just a few impacts of a weak AMOC are severe winters in northern Europe, major changes in rainfall patterns and drought over many parts of the world, warming of the southern hemisphere and melting of Antarctica, and less uptake of CO2 by the ocean. A recent study published in Nature shows that both the rate and the magnitude of temperature change are positively correlated with the rate at which species go extinct. The top graph shows temperature change, the middle, the rate at which temperature changes, and the bottom, the rate at which species go extinct. There were 5 major mass extinctions in the last 500 million years. They're shown in the gray bars, which don't show up very well, but they're numbered 1 to 5. So you can see that there's pretty good correlations between these 3 graphs, with the peaks lining up fairly well in all 3, especially the rate of species extinction and the rate of temperature change. Just so we're on the same page, do we really understand what a mass extinction is? 75%. We're not talking a couple hundred species. We're talking a mass extinction is 75% of Earth species, at least. The paper's findings predict that a temperature increase of 5.2 degrees C above pre-industrial level at the present rate at which temperature is increasing will result in a mass extinction equal to any of those of the Phanerozoic era, those last 5. We are now 1.4 degrees C higher, warming at a rate of about 2 degrees per century. If everything continues as it is, we'll hit that 5.2 in about 200 years. So, what does the future hold? Will we return to icehouse conditions? Or have we tipped the scales enough to enter and remain in a greenhouse world? Much of this depends on what the maximum CO2 is going to be. What peak are we going to hit, and how fast can it be removed? The image on the right shows ice mass changes in Antarctica, March 2025, compared to what it looked like in April 2002. Okay. The colors in blue indicate ice gain, colors in white, no change, and the warm colors show ice loss. The deeper the color, the more the ice loss. A 2016 study published in the journal Science presents data that indicate that at CO2 levels above 600 ppm will cause the Antarctic ice sheet to cross a tipping point and start a deterioration that will be irreversible. It is possible that Western Antarctica has already crossed a tipping point. A 2023 publication in Geophysical Research Letters gives even grimmer news for the Greenland ice sheet. Their data show that much of the ice sheet is already at or past its tipping point, and it will not be able to begin to grow or expand unless CO2 levels are below 300 ppm. So the future outlook is that Earth will enter a greenhouse phase. If the rate and removal of atmospheric CO2 is fast enough so that the tectonic plates are basically where they are now, then we should be able to return to an icehouse world. How many glacial, interglacial cycles we miss depends on when CO2 levels return to less than 300 ppm. If removal is slow and tectonic plates and other Earth systems are no longer configured to support an ice house Earth, then Earth will remain in a greenhouse phase until some point far, far in the future when the conditions are once again configured to favor ice house. We can learn from Earth history how our climate system works. We can learn how sea level changes, how atmospheric and ocean circulations change. We can foresee what these changes will mean to the dislocation and extinction of species, and for human civilization, food production, water resources, and extreme weather. Study of paleoclimate makes it very clear that humans are now the dominant force of climate change on Earth. What it can't teach us are clear, easy solutions to what we have wrought.
Hi, Vicki. Now I'll ask my serious science question. In your graph that you showed the abrupt change from glacial to interglacial, I was pondering what's happening at that time, and I thought to myself, well, certainly at that glacial period, the maximum amount of water is tied up in ice. Mm-hmm. So the flip side of that is that the oceans must be at their lowest footprint, the lowest area of oceans. Mm-hmm. And so now that battery that would ordinarily absorb heat is now not absorbing heat, and there's more impact of air melting that ice that's no longer insulated by the oceans. What are your thoughts on that?
The thing is, they hit their maximum, you know, a couple times if you look at the curve, a lot, tens of thousands of years before the termination. The terminations seem to need that extra trigger of warmer poles, that little more heat coming in from the sun to start melting. That's what it looks like. And then once you get that, all those feedback loops cascade one after another, and the ice melts very quickly. It seems to go probably in pulses. You might have a vast amount of melting, then it seems to stop for a while, and then you have vast collapse over, you know, within like 2,000 years. So these collapses occur very, very quickly. But it does take a long time for that ice to accumulate because you do have warmings, coolings, warmings, coolings. The interglacials seem to stay fairly warm.
What are your thoughts on the current condition of the permafrost? I keep reading articles about that holds an enormous amount of methane. And do you see that as being a big driver or not?
It's definitely being added. I don't know the rate at which it's being added because it can stay in the atmosphere for 12 to 16 years. So if it's coming in small amounts, it's definitely contributing to the heat. There have been times in Earth history where you see sometimes these giant spikes of climate, you know, just short-term giant spikes. And some of those have been thought to be related to melting of methane ice in the oceans, usually not just from warming, but from actually collapse of landslides that collapse the things and expose these things to the water. And then methane just bubbles out and you get this tremendous spike and very rapid heating.
I hope this is being recorded because I'm going to need to listen to it a few more times. Two things, actually. The rate and size of forest fire increasing exponentially around the world. That not only emits the CO2 that we sequestered, but it also slows the process of being able to process CO2 into oxygen. Has that factor been included in the modeling?
They have. Some people have also looked at the particulate matter of things, but because it has such a short residence time in the atmosphere, it doesn't have any effect on the kind of global temperatures that we're talking about. But yes, the addition of CO2 is a big factor, and I know they are including it in some of the models. I don't know the details on what it looks like, but whatever it is, it makes it look worse.
Yeah. And is there any kind of state-of-the-art thinking, theoretical thinking, hoping about capture? What are the best technologies for CO2 capture and sequester?
I know that there are different companies that are looking at that, and to be honest, that's about the only thing that can save us, is because if there's no natural mechanism that we know of that can remove the amount of excess CO2 that we've added. So the only thing that could help us is if we're smart enough to figure out something that could pull CO2 out of the atmosphere. I know there are different things they're looking at. They've tried to seed the ocean in different ways to make more carbonate minerals. There's all sorts of different things they've looked at. As far as I know, none of them are commercially viable or maybe even scientifically viable on a big scale.
I'm wondering for our climate change denier friends and relatives, it sounds like the scale, for natural events, because that's what they say, right? Oh, it's changed. We had an ice age when humans were around. But the natural scale would be like at the least like 10,000 years. But this scale is like 200 years. Is that a fair? Like, what would you say to someone who?
It's the rate at which we're adding CO2. Yes, I mean, you've seen natural cycles cause climate change. Earth heats and cools, that hits the feedback loops. You get change without humans. But what's happened now is that it's the rate at which we've added CO2 to the atmosphere. That's just not been seen ever before, as we know of in Earth history. So that's what the thing is. It's the rate. Okay, and everything. If the rate's higher, Earth gets warmer. Yes, it puts more water vapor in the atmosphere, but it wouldn't be there if we hadn't added the CO2.
Hi, this is Ken. In the 1700s, we had a period known as the Little Ice Age, when it got very cold in Europe, North America, and that lasted, 200 years maybe. Is it possible that was the beginning of, the slow beginning of the start of the next ice age, which was forestalled by the adding of CO2, by industrialization and planting of rice, etc.?
No, the cause of the Little Ice Age, I was going to include that in my talk, I just didn't have enough time. But it was probably the biggest influence. There were multiple influences on it, but probably the biggest one was a slowing down of amok.
Hi, I'm Lisa, and I was just thinking about during the 1960s. I grew up in Los Angeles. And it seems like smog levels were much higher than they are now. And I was wondering if anything could be done to lower the CO2 levels today.
Well, smog isn't CO2, so it's more particulate matter and ozone it's called. So getting rid of smog isn't changing the CO2.
This may be totally unrelated, but with all the climate changes that are occurring and the discussion of plate tectonics, you hear so much in Oregon about the great subduction earthquake that could be disastrous on Oregon and many structures. Is there any projection in terms of when that could occur, or how many 100 years, or what would be the time frame?
I think it'll occur in about 16.2 years. No, we don't know when it's, we just know that statistically the probability is that it will be relatively soon. What that means, 30 years, 100 years, you know? Yeah, but it's not going to be a direct cause of climate change. It's not going to alter our tectonic positions to disconfigure icehouse Earth.
So, Vicki, this may be a rhetorical question, but it has some science relationship to what you've shared, and that is, as CO2 rises in the atmosphere, it displaces other gases and causes changes. A good example is when we were born, the atmosphere had like 20% oxygen. It's now about, what, 14%? And I wonder if anybody's correlated that. I mean, since our brains need oxygen, is they correlated that with intelligence?
I don't know. Addition of CO2 doesn't necessarily mean you have to take something out. You can make air denser. So you don't necessarily have to remove it, but, you know, and remember, even at the rate at which we're going, it's still a really tiny volume. Yeah. So, yeah.
In answer, the oxygen levels have not gone down that much. Oxygen levels are still basically where they were. They are going down, but it is in the hundredths of a degree. You know, because of what Vicki said, because the CO2 is, you know, such a small part of the atmosphere, it's not eating up that much.
Mark again. I just wanted to add to the answer about the wildfires. One thing that wasn't mentioned in the answer was the reduction in albedo as all of that ash falls onto the nice white ice and turns it black. They're modeling that.
That is modeled, yes.
Any more questions? Okay. Thank you, Vicki.